Long before there were stars or light or even space as we recognize it, the universe was already preparing something quietly essential. Not an explosion you could hear, not a flash you could see, but a subtle arrangement of energy that would one day become everything you know. Tonight, we follow that quiet beginning, the moment the very first atom formed, and how that single, delicate structure changed the entire direction of reality. If this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe is a quiet way of keeping these slow explorations alive, and I thank you for it. Now, with no rush at all, we turn the page. Part 1. What existed before atoms? Before the first atom could ever take shape, the universe was a place without structure. No chemistry, no solids, no light traveling freely through space. There was only an intense, searing sea of energy, so hot and dense that nothing could stay together for long. Protons and electrons existed, but they could not touch. The universe itself was too restless, expanding too fast, vibrating too violently. To understand the first atom, you must first imagine a cosmos where connection was impossible, where even the idea of matter had not yet settled into form. To picture this moment, you have to let go of familiar scales. There were no stars overhead, no planets beneath, no darkness between points of light. Space itself was filled everywhere, at every point, with heat and radiation. Temperatures were measured not in thousands or millions of degrees, but in billions. Energy dominated everything. Matter, as we know it, was only a temporary suggestion, forming and dissolving faster than any structure could survive. In the earliest moments after the Big Bang, the universe behaved less like a place and more like a process. Particles flickered into existence and vanished again, governed by quantum rules that allowed brief appearances before annihilation. Even the concept of a particle was unstable. Quarks and gluons moved freely in a dense plasma, never locking together long enough to form protons or neutrons. Physicists call this state the quark-gluon plasma, a phase of matter so extreme that it hasn't existed naturally since the first microseconds of cosmic time. As the universe expanded, it cooled, not suddenly, but steadily, predictably, following simple physical laws. Expansion meant dilution, cooling meant possibility. After about 1/1,000,000th of a second, quarks began to bind together, forming protons and neutrons for the first time. This was the universe's first hint of permanence. But even then, atoms were still impossibly far away. For hundreds of thousands of years, the universe remained too hot for electrons to settle down. Free electrons moved at tremendous speeds, constantly scattering photons. Light existed, but it could not travel freely. Every photon was quickly absorbed or deflected, trapped in an endless game of collisions. The universe was opaque, more like the inside of a star than the open cosmos we see today. If you were somehow present then, there would be no sky to look into, no direction to gaze. Light could not form beams. Distance had little meaning. Everything was immersed in the same glowing fog of radiation. Time moved forward, but slowly, measured by cooling rather than clocks. Protons and neutrons did manage one early act of construction. Within the first few minutes, as temperatures dropped below 1 billion degrees, they combined to form the nuclei of hydrogen and helium. This process, known as Big Bang nucleosynthesis, created nearly all the hydrogen that still fills the universe today, along with most of its helium. But even here, atoms were incomplete. These nuclei were naked, positively charged, unable to capture electrons. For the next 380,000 years, the universe lived in this suspended state. Nuclei existed, electrons existed, photons existed, but they could not coexist peacefully. Any attempt by an electron to bind to a nucleus was immediately undone by the intense heat. The energy of the surrounding radiation was simply too high. Bonds could not survive. This long delay is one of the quiet truths of cosmology. The universe had all the pieces of atoms very early on, but it took patience for conditions to become gentle enough for assembly. Creation in this sense was not dramatic. It was restrained. It waited. As expansion continued, temperatures fell to about 3,000 degrees Kelvin. That number may still sound hot, but compared to the earlier universe, it was calm. At this threshold, something remarkable happened. Electrons slowed enough to be captured by protons. For the first time, stable hydrogen atoms formed. This event is called recombination, though nothing was recombined in the everyday sense. It was simply the first time electrons could stay. When they did, the universe changed instantly and forever. With electrons bound into atoms, photons were suddenly free. Light no longer scattered constantly. It began to travel in straight lines across space. The universe became transparent. That ancient light is still with us today, stretched and cooled by expansion into what we now call the cosmic microwave background. It is the oldest light we can observe, a faint afterglow from the moment atoms first existed. This is why the first atom matters so deeply. It marks the transition from a universe dominated by radiation to one governed by matter. Before atoms, structure was impossible. After atoms, complexity became inevitable. Once hydrogen atoms filled space, gravity could begin its slow work. Tiny differences in density, left over from quantum fluctuations in the early universe, were no longer erased by radiation pressure. Matter could clump, clouds could form. Over millions of years, these clouds collapsed into the first stars. But that story comes later. For now, it's enough to sit with this quiet threshold. The moment when the universe cooled just enough to allow connection. When electrons finally slowed their restless motion and settled into orbit. When matter, for the first time, held together. Even now, as you breathe quietly, those same processes remain written into reality. Every atom in your body follows the same rules established in that early epoch. The hydrogen in your cells was born in those first minutes. The electrons that define chemistry learned how to bind during recombination. The laws have never changed. What's most striking is how gentle this transformation was. No explosion marked the birth of the first atom. No flash announced it. The universe simply crossed a temperature threshold and connection became possible. The most profound changes in physics often arrive this way, not with noise, but with conditions finally becoming calm enough. As the cosmos cooled, it didn't rush. Expansion continued, time stretched, space grew vast, and within that growing quiet, matter found stability. The first atom did not appear alone. It appeared everywhere, almost at once, as the entire universe crossed the same boundary together. In that sense, the birth of atoms was the first truly global event, shared across all of space. And with that event, the universe gained memory. Atoms could store information in their arrangements. They could form molecules. They could participate in chemistry. Eventually, they could assemble into stars, planets, oceans, and living cells. All of that waited patiently inside this moment. Before atoms, the universe was energy without structure. After atoms, it became a place where complexity could slowly unfold. That single transition changed everything, not by adding something new, but by allowing what already existed to finally stay together. And as we continue this quiet journey, one question naturally rises from the darkness that came before light. How did that first simple atom eventually give rise to the staggering diversity of matter we see today? Part 2. How hot was the early universe really? In its earliest moments, the universe was hotter than the core of any star that would ever exist. Temperatures exceeded billions of degrees, and energy ruled completely over matter. At these extremes, particles collided endlessly, breaking apart as quickly as they formed. Nothing could remain intact. The universe was young, but it was already vast, stretching outward in all directions, cooling slowly, patiently, as time began to take its first measured steps forward. To understand just how hot this early universe was, you have to let go of everyday intuition. Even the hottest places we know today, stellar cores burning with nuclear fire or the surfaces of newly formed neutron stars, are gentle by comparison. In the first fractions of a second after the Big Bang, the universe reached temperatures of trillions of degrees. At those energies, the distinction between matter and energy blurred almost completely. Particles did not behave like stable objects. They were fleeting patterns, appearing and vanishing in a restless glowing sea. As you breathe quietly right now, your surroundings feel calm and solid. But early on, the universe had no such stillness. Every region of space was filled with radiation so energetic that it shattered any attempt at structure. Photons were not passive messengers of light, they were powerful agents of change, colliding with particles and tearing them apart. Protons could exist, but electrons could not stay bound to them. Any attempt at connection was immediately undone by heat. This era is known in cosmology as the radiation-dominated universe. Energy density was controlled not by matter, but by light itself. Photons outnumbered particles by billions to one, and their pressure shaped the expansion of space. The hotter the universe was, the faster everything moved, and the more violent every interaction became. Temperature, in this sense, was not just a number. It was a measure of how chaotic reality itself had become. In the earliest instance, less than a second after the beginning, temperatures were so extreme that even protons and neutrons could not exist as stable entities. Quarks and gluons, the fundamental constituents of nuclear matter, floated freely in what physicists call a quark-gluon plasma. This state of matter has been recreated briefly in particle accelerators on Earth, but only in volumes smaller than an atom and lasting for fractions of a second. Back then, it filled the entire universe. As the universe expanded, it cooled. This cooling was not sudden or dramatic. It was steady and inevitable, driven by the simple geometry of expansion. As space stretched, energy spread out. Wavelengths of radiation grew longer. The violent jitter of particles softened, just enough for new possibilities to emerge. Cooling was not the absence of heat, but the gradual lowering of its dominance. After about 1 microsecond, the universe cooled enough for quarks to bind together, forming protons and neutrons. Even then, temperatures remained around 1 trillion degrees. Nuclear particles existed, but atoms were still impossible. Electrons, though present, were far too energetic to settle into orbits. Any attempt at bonding was immediately disrupted by high-energy photons crashing through space. If you could observe the universe at this time, there would be no darkness, no stars, no empty voids. Every direction would glow uniformly. Light had no place to travel freely because everything was light. Space was opaque, filled with constant scattering. Photons collided endlessly with charged particles, unable to move far without interruption. Vision, in any familiar sense, could not exist. This early heat also shaped the arrow of time. High temperatures meant high entropy, a state of intense disorder. Yet paradoxically, the universe began in an incredibly uniform condition. Temperature was almost the same everywhere, differing by only tiny fractions. These minuscule variations, 1 part in 100,000, were enough to seed everything that would later form: galaxies, stars, planets, and eventually life. Heat smoothed the universe, but it also preserved the faintest ripples of difference. As expansion continued, the universe passed through key thermal milestones. After a few minutes, temperatures dropped to about 1 billion degrees, cool enough for the first atomic nuclei to form. Hydrogen and helium nuclei emerged through a process called Big Bang nucleosynthesis. But even now, atoms themselves were still forbidden. The universe remained a plasma, an electrically charged fog where electrons and nuclei could not unite. For hundreds of thousands of years, this hot plasma filled all of space. Temperatures steadily declined from millions of degrees to mere thousands. Compared to stars, this was still incredibly hot. Compared to the early universe, it was a profound cooling. The pace was slow, almost meditative. Expansion stretched time as it stretched space, allowing complexity to wait patiently for the right conditions. At around 300,000 years after the beginning, the universe cooled to roughly 3,000 degrees Kelvin. This number may sound modest, but it marked a cosmic turning point. At this temperature, electrons finally slowed enough to bind to nuclei. For the first time, atoms could exist. Hydrogen formed, helium followed. The first stable structures emerged, not from force, but from calm. This moment is known as recombination, though it was truly a first combination. With atoms in place, photons were suddenly free to travel long distances without constant scattering. Light decoupled from matter, the universe became transparent. The radiation released at that moment still fills space today as the cosmic microwave background, cooled now to just 2.7 degrees above absolute zero. It is the faint afterglow of an ancient heat, stretched thin by billions of years of expansion. When you lie quietly in the dark, surrounded by stillness, it is hard to imagine that the universe was once too hot for atoms to exist. Yet every atom in your body carries that memory. Its components were forged in a cosmos where temperature dictated what was possible and what was forbidden. Heat was not an obstacle. It was the shaping force that determined when matter could finally settle into form. Temperature, in cosmology, is inseparable from time. To ask how hot the universe was is also to ask how old it was. Each degree of cooling marked a new chapter, a new set of rules. When the universe was hotter, symmetry reigned, forces were unified, particles behaved almost interchangeably. As it cooled, distinctions emerged. Electromagnetism separated from nuclear forces. Matter gained identity. Complexity unfolded step by step. Even now, the universe continues to cool. Expansion has not stopped. Space keeps stretching and energy keeps thinning. Stars burn, but their warmth is local, temporary. On the largest scales, the cosmos drifts toward colder, darker states. The intense heat of the beginning was not wasted. It was transformed into structure, into motion, into the quiet background against which everything else exists. So when we ask how hot the early universe really was, the answer is not just a number. It is a story of extremes softening into balance, a story of a universe that began too energetic for matter, too restless for connection, and slowly learned how to cool. And as this quiet cooling continued, one final question remained, waiting patiently in the dark. When the universe was finally calm enough for atoms to exist, which one would form first? Part 3. Why couldn't electrons attach to nuclei at first? Even though protons and electrons were present, they lived separate lives. The energy filling space was so intense that any attempt at bonding was instantly torn apart. An electron drawn toward a proton would be knocked away by a passing photon almost immediately. The universe was bright, opaque, and turbulent. Light itself could not travel freely. Everything was constantly interacting, colliding, and dissolving again into motion. To understand why this separation persisted, you have to imagine the universe not as empty space, but as a dense, glowing ocean. Every region of space was flooded with radiation. Photons were everywhere, carrying enormous energy, striking particles from all directions. There was no quiet corner where two particles could linger together. No stillness, no shelter. Even the smallest attempt at structure was overwhelmed by heat and motion. In this early era, temperature was not just a number. It was a measure of how violently the universe behaved. When scientists say the universe was thousands of degrees, or millions or billions, what they are really describing is energy density. Energy packed so tightly that particles could not slow down. Every electron raced through space at incredible speeds. Every proton vibrated, jostled, and collided. Under those conditions, attraction could not win. An electron is drawn to a proton by the electromagnetic force, one of the fundamental forces of nature. It is powerful, but it is not infinite. In a cooler universe, that attraction allows electrons to settle into stable orbits, forming atoms. But in the early universe, photons carried enough energy to overpower that attraction. The moment an electron tried to settle, a photon would strike it and knock it free again. Bonding was not forbidden by the laws of physics. It was simply outpaced by chaos. This state of separation is known as a plasma. A plasma is matter so hot that electrons are stripped away from nuclei, leaving a soup of charged particles. Today, plasmas still exist in lightning bolts, in neon signs, and in the interiors of stars. But the early universe was a plasma on a cosmic scale. Every cubic centimeter of space behaved like the inside of a star, except there were no stars yet, only the universe itself. In this plasma-filled cosmos, light could not move freely. Photons did not travel long distances in straight lines. Instead, they were constantly absorbed and re-emitted, scattered and redirected. The universe was opaque. not transparent. If you could have existed then, there would have been no horizon, no distant view. Light from even a short distance away would never reach you uninterrupted. The universe glowed uniformly, but nothing could be seen clearly. Time passed, though not in the way we usually imagine it. Seconds stretched into minutes, minutes into thousands of years. All the while, the universe expanded. Expansion is not motion through space, but of space itself. As space stretched, energy diluted. Temperatures fell, slowly, patiently. The universe did not cool because it lost heat to something else. There was nothing else. It cooled because it grew larger. As the temperature dropped, the balance of power began to shift. Photons lost energy. Collisions became slightly less violent. Electrons still moved quickly, but not quite as wildly. The electromagnetic attraction between electrons and protons did not change. It was constant. What changed was the environment. The universe was becoming calmer, not suddenly, but gradually, like waves settling after a storm. For hundreds of thousands of years, this gradual cooling continued. Protons and electrons remained separate, but the gap between possibility and reality narrowed. Each moment, the average photon carried a little less energy. Each collision became a little less destructive. The universe was quietly preparing for something it had never done before. This long wait is easy to overlook, but it matters. The first atoms did not form immediately after the Big Bang. They required patience on a cosmic scale. Physics needed time to create conditions where stability could emerge. The universe had to expand enough, cool enough, and slow enough for attraction to finally succeed. Eventually, a critical threshold was crossed. The average energy of photons dropped below the energy required to knock electrons away from protons. For the first time, when an electron approached a nucleus, it could stay. Not forever at first. Some bonds still broke, but enough held. And once they did, something profound changed. This moment is known as recombination, though it was not truly a recombining. It was the first combining. Electrons and nuclei joined to form neutral atoms, primarily hydrogen and helium. The universe, which had been ionized and glowing, began to turn transparent. Light was suddenly free. Photons that had been trapped for hundreds of thousands of years were released. They began traveling through space in straight lines, no longer scattered at every step. Those same photons still exist today, stretched by the expansion of the universe into microwaves. We call them the cosmic microwave background, a faint echo of the moment electrons finally attached to nuclei. But at the time, there was no echo. There was only a quiet transformation. The universe dimmed, not into darkness, but into clarity. Structure was now possible. Chemistry could begin. Matter could persist without being torn apart instantly. The first atoms did not announce themselves with explosions or light shows. They formed silently, everywhere at once. It is worth pausing here, because this was not just a chemical event. It was a change in the behavior of the universe itself. Before atoms, the universe was dominated by radiation. After atoms, matter began to take the lead. Gravity could now act more effectively on neutral atoms, allowing them to clump together over time. Without electrons attaching to nuclei, there would be no stars, no planets, no molecules, no life. From your perspective now, this ancient delay may feel distant, abstract, but it shaped everything you know. The air you breathe exists because electrons learned to stay. The light you see exists because photons were once set free. Even the fact that the universe has a visible structure traces back to this moment when chaos finally loosened its grip. And yet, even after atoms formed, the universe was still simple. There were no complex elements yet, no carbon, no oxygen, just hydrogen, helium, and traces of lithium. Simplicity ruled, but it was a new kind of simplicity, one built on stability rather than violence. As you rest here, listening, it's worth reflecting on how fragile that balance was. A slightly hotter universe and atoms might never have formed. A slightly different expansion rate, and electrons might still be wandering free. The universe did not rush into complexity. It waited until the conditions were just right. This is one of the quiet lessons of cosmology. Structure does not emerge from force alone. It emerges when forces are allowed to balance, when motion slows just enough, when energy yields, not completely, but gracefully. In the next part of our journey, we'll follow what happened once atoms finally existed, how darkness filled the universe, how gravity began its slow work, and how, from these first simple bonds, everything else patiently unfolded. Part 4. When did the universe finally cool enough for stability? As expansion continued, something gentle began to happen. Over hundreds of thousands of years, the universe cooled just enough for chaos to loosen its grip. Temperatures dropped below a critical threshold, not suddenly, not dramatically, but gradually. This cooling was not an event so much as a long exhale, and within that exhale, the conditions for stability quietly emerged. To understand this moment, you have to let go of the idea of a ticking clock or a sudden switch being flipped. The early universe did not decide to become calm. There was no boundary line where disorder ended and structure began. Instead, the universe simply kept expanding, and as it did, the average energy of everything within it slowly decreased. Space stretched. Photons lost energy as their wavelengths lengthened. What had once been a blinding, violent sea of radiation began, almost imperceptibly, to soften. For the first few minutes after the Big Bang, temperatures were unimaginably high, hot enough to forge the first protons and neutrons. But even after those earliest nuclear reactions ended, the universe remained far too hot for anything like atoms to exist. For hundreds of thousands of years, it was still filled with a dense plasma, a glowing fog of free electrons, atomic nuclei, and high-energy photons, all colliding constantly. Matter and radiation were tightly coupled, locked together in an endless exchange of energy. As the universe expanded, its temperature followed a simple but powerful rule. When space doubles in size, the temperature drops, not because heat escapes anywhere, but because energy spreads out over more room. This cooling was steady and inevitable, governed by the laws of thermodynamics and the geometry of space-time itself. Every second that passed made the universe slightly calmer than the second before. There came a point, about 380,000 years after the beginning, when the average temperature fell below roughly 3,000 Kelvin. This number may sound abstract, but it marks a profound threshold. Above it, electrons could not remain bound to nuclei. Below it, they finally could. This was the moment when the universe became cool enough for stable atoms to exist, at least in principle. What made this threshold so important was the balance between energy and attraction. Protons and electrons are drawn to one another by electromagnetism, but in a hot environment, thermal energy overwhelms that attraction. Photons carried enough punch to knock electrons loose the instant they tried to settle into orbit. As long as the universe stayed hotter than this critical point, matter could not assemble into anything more complex than bare nuclei and free electrons. As cooling continued, that balance slowly tipped. Photons became less energetic, collisions became less destructive. The electromagnetic pull between particles began to matter again. For the first time since the universe began, it became possible for electrons to stay close to nuclei without being immediately torn away. Stability was no longer forbidden by the ambient conditions of space. This transition is known in cosmology as recombination, though the name is slightly misleading. Electrons and nuclei were not combining again after a previous union. They were meeting for the first time under conditions that allowed them to remain together. Hydrogen atoms formed as electrons settled into stable orbits around protons. Helium nuclei captured electrons as well. The first true atoms quietly came into existence. But recombination was not instantaneous. It unfolded over tens of thousands of years. Even as atoms began to form, high-energy photons were still present, still capable of ionizing some fraction of matter. The universe hovered in a delicate intermediate state, part plasma, part neutral gas. With each passing millennium, however, the balance shifted further toward stability. One of the most remarkable consequences of this cooling was the sudden freedom of light. Before atoms formed, photons could not travel far without scattering off charged particles. The universe was opaque, like a dense fog. But once electrons became bound into atoms, that fog lifted. Neutral atoms interact far less strongly with radiation. Photons were suddenly free to move through space without constant interruption. This moment, when light first began to travel freely, is called decoupling. It marks the birth of the oldest light we can still observe today, the cosmic microwave background. These photons have been traveling almost uninterrupted for nearly 14 billion years, cooling and stretching along with the universe itself. They are the quiet afterglow of the moment stability first took hold. If you could have been present, if such a thing were possible, the change would not have looked dramatic. There would have been no flash, no sudden darkness, no clear boundary. The universe would have simply grown dimmer, calmer, more transparent. The constant roar of interactions would have softened into a quieter hum. For the first time, space would have felt open rather than crowded. This cooling did more than allow atoms to exist. It fundamentally changed the future of the cosmos. Once neutral atoms formed, gravity could begin to work more effectively. Tiny variations in density, imperfections left over from the early universe, were no longer smoothed out by intense radiation pressure. Matter could start to clump, very slowly, under its own weight. These early clumps were subtle, barely noticeable against the vastness of space. But given enough time, gravity amplifies small differences. Regions with slightly more matter pulled in more material. Over millions of years, these gentle imbalances grew into clouds, then into the seeds of galaxies. None of this would have been possible without the initial cooling that allowed atoms to exist in the first place. What's striking is how precise this window of stability had to be. If the universe had expanded just a little faster, matter might have thinned out too quickly for atoms to form efficiently. If it had expanded more slowly, radiation might have kept matter ionized for much longer, delaying structure. The universe did not aim for balance, but its physical laws naturally guided it there. As you breathe quietly now, it's worth remembering that this stability was not guaranteed by intention or design. It emerged from simple rules applied over immense scales of time and space. Expansion led to cooling. Cooling allowed binding. Binding allowed complexity. Each step followed calmly from the last, without urgency, without awareness. Even after atoms formed, the universe was still dark. There were no stars yet, no galaxies, no visible sources of light beyond the fading afterglow of creation. It would take hundreds of millions of additional years for gravity to gather enough matter to ignite the first stars. But the foundation had been laid. Stability, once achieved, could build upon itself. In a sense, this cooling marked the universe's transition from raw potential to quiet preparation. Energy no longer dominated every interaction. Matter gained the ability to linger, to persist, to remember its form from one moment to the next. The universe had learned how to hold still, at least a little. As we move forward in this story, one gentle question remains. Once atoms existed, once stability was finally possible, which atom formed first, and why did that simplest structure go on to shape everything that followed? Part 5. What exactly was the first atom? The first atom was simple, just one proton and one electron, bound together by electromagnetism, hydrogen, no complexity, no variety. Yet this simplicity carried immense consequence. For the first time, matter could remain intact. The universe had discovered how to hold itself together, even if only in the smallest possible way. To understand why this moment mattered so deeply, it helps to slow down and look closely at what an atom truly is. An atom is not a solid object in the way we imagine everyday things. It is mostly empty space. A tiny, dense nucleus sits at its center, while electrons exist as faint, probabilistic clouds around it. The forces that bind these pieces together are invisible, but precise. And for hundreds of thousands of years after the universe began, those forces could not complete their work. When the first atom finally formed, it was not dramatic. There was no flash, no sudden transformation visible across the cosmos. It happened quietly, everywhere at once. As the universe cooled and expanded, electrons began to slow. Photons lost energy. The constant violence of collisions softened. And in that gentler environment, an electron could finally remain close to a proton without being torn away. This moment is known in cosmology as recombination, though the name is slightly misleading. It was not a recombination of previously formed atoms, but the first true combination of charged particles into neutral matter. Around 380,000 years after the Big Bang, the universe crossed a subtle threshold. The temperature dropped to about 3,000 Kelvin, still unimaginably hot by human standards, but cool enough for stability to emerge. At that temperature, hydrogen atoms began to form in vast numbers. Each one was identical, one proton, one electron. No neutrons were required for the most common form of hydrogen. This made it the simplest atom possible, the lightest building block matter could create. And because the laws of physics are uniform, this same process occurred everywhere, filling the universe with a nearly uniform sea of neutral hydrogen. This uniformity is important. The first atoms did not appear as isolated curiosities. They appeared as a cosmic background, a smooth foundation upon which everything else would later build. Before atoms, the universe was a glowing plasma, opaque and bright, scattering light endlessly. After atoms formed, something profound changed. Light was finally free to travel. When electrons bound to protons, they no longer scattered photons as efficiently. The universe became transparent. Light that had been trapped since the earliest moments could now move freely through space. That ancient light still exists today. It has stretched and cooled over billions of years, becoming what we now call the cosmic microwave background. It is the oldest light we can observe, a quiet echo of the moment atoms first formed. In this sense, the first atom did more than create matter. It revealed the universe to itself. For the first time, information could travel unimpeded across vast distances. Structure could begin to grow without being constantly erased by radiation. Gravity, which had always been present, could finally start shaping matter in a lasting way. Hydrogen atoms, though simple, have subtle internal rules. The electron does not orbit the proton like a planet around a star. Instead, it exists in discrete energy states described by quantum mechanics. These allowed states are what give atoms their stability. An electron can only exist at certain energies, and once it settles into the lowest available state, it cannot fall further. This quantum limitation is what prevents atoms from collapsing entirely. This means that the first atom was not just a physical object, it was a balance point between forces. Electromagnetism pulled the electron inward. Quantum mechanics set a boundary. Together, they created permanence. For the first time, the universe contained things that could endure. Almost all of these first atoms were hydrogen. A small fraction, about 1 in every 12 nuclei, formed helium instead. Helium nuclei contained 2 protons and 2 neutrons, and once electrons joined them, they formed the second simplest atom. But heavier elements could not yet exist. The universe was not dense enough, nor energetic in the right way to build them. That would come much later, inside stars. So in its earliest atomic age, the universe was simple and quiet. No stars, no galaxies, no planets, just a vast, dark expanse filled with neutral hydrogen and helium gas. This period is sometimes called the Cosmic Dark Ages, not because it was ominous, but because there were no sources of visible light yet. The universe had become transparent, but nothing was shining. Yet within this stillness, everything necessary for complexity was already present. Hydrogen atoms could interact. They could drift together under gravity. Tiny differences in density, seeded much earlier, began to grow. Where matter was slightly denser, gravity pulled more matter in. Over millions of years, these regions would collapse, heating up, eventually igniting the first stars. All of chemistry traces back to this moment. Without the first atom, there can be no molecules. Without molecules, no clouds, no stars, no planets. Even water, with its graceful simplicity, depends on hydrogen's willingness to bond. Carbon-based life, the complexity of DNA, the chemistry of thought itself, all begin with that first successful pairing of 1 electron and 1 proton. It is easy to overlook hydrogen because it feels unremarkable. It is invisible, tasteless, abundant. But its abundance is precisely what gives it power. Roughly 3/4 of all ordinary matter in the universe is still hydrogen. Every star burns it. Every galaxy is threaded with it. The most ancient structures we can observe are still shaped by its presence. Even now, as you rest and listen, hydrogen atoms surround you. They exist in the water within your body, in the air you breathe, in the distant stars whose light reaches your eyes after traveling for millions of years. Each one is governed by the same rules established when the first atom formed. The beauty of this moment is not in its spectacle, but in its restraint. The universe did not rush. It cooled patiently. It allowed conditions to align. And when they did, matter settled into a form that could persist. From chaos emerged the possibility of memory, of structure, of history. As we continue this quiet journey, another question begins to rise naturally from this first success. Once atoms could exist, what happened next? How did these simple particles gather, ignite, and transform into the stars that would one day forge everything else? That question waits just ahead as the universe takes its next slow step forward. Part 6. How did recombination change the universe forever? This moment is known as recombination, though nothing was truly recombining for the first time. It was the universe's first successful attempt at neutrality. Electrons settled into stable orbits around nuclei, forming atoms that no longer scattered light endlessly. Space, once opaque, became transparent. Light was finally free to travel without constant interruption, carrying information across vast distances. Before this moment, the universe was filled with a glowing fog. Every direction you looked, every possible path light could take, was blocked almost immediately. Photons did not move in straight lines. They ricocheted constantly, colliding with free electrons again and again, never traveling far enough to form a clear view of anything. The cosmos was bright but blind, energetic but unreadable. Recombination quietly changed all of that. To understand why this mattered so deeply, it helps to imagine the universe not as empty space, but as a crowded room. Before recombination, the room was packed with restless particles. Electrons moved freely, charged and reactive, constantly intercepting light. Every photon trying to cross the room was stopped, scattered, redirected. No signal could survive long enough to carry meaning. There was motion everywhere, but no clarity. As the universe expanded, its temperature continued to fall. Expansion does not just stretch space, it dilutes energy. With every passing moment, the average energy of photons dropped. Eventually, those photons no longer carried enough force to rip electrons away from protons once they bonded. This threshold mattered. Above it, atoms could not survive. Below it, they could finally endure. This transition happened roughly 380,000 years after the Big Bang. By human standards, that sounds unimaginably ancient. By cosmic standards, it was still infancy. The universe was less than 1/1,000,000th of its current age. Yet in that brief window, its character changed forever. When electrons settled into stable relationships with nuclei, the universe underwent a phase shift. Charged chaos gave way to neutral calm. Free electrons vanished in vast numbers, locked into atoms. With fewer charged particles roaming through space, photons suddenly found fewer obstacles. The fog lifted. The room emptied. Light began to move freely for the first time. This is why recombination is sometimes described as the moment the universe became transparent. Not because light was created then, but because light was finally released. Photons that had been trapped since the earliest moments were suddenly free to travel uninterrupted across the cosmos. Many of those very photons are still traveling today. If you could somehow see the universe at that instant, you would not witness fireworks or sudden brilliance. There was no flash, no sound, no sharp boundary. Recombination was quiet, gradual, like frost forming slowly on a window pane. Atoms assembled one by one across expanding space until neutrality became the rule rather than the exception. This newly liberated light carries a name now. We call it the cosmic microwave background. It is the oldest light we can observe, a faint afterglow that fills all of space. It does not come from stars or galaxies, which did not yet exist. It comes from the moment the universe first allowed light to travel freely. Today, that light has cooled dramatically. What was once a searing glow of thousands of degrees has been stretched by cosmic expansion into microwave wavelengths just a few degrees above absolute zero. Yet it still surrounds you. Even now, as you lie still, your body is gently bathed in ancient photons released during recombination, older than any structure in the universe. Recombination also changed the future of matter itself. Once atoms existed, chemistry became possible. Not immediately complex chemistry, but the potential for it. Neutral atoms could clump together under gravity without being torn apart by radiation pressure. They could begin to gather slowly, patiently, forming denser regions in an otherwise smooth universe. Before recombination, gravity was fighting against radiation. Photons carried momentum. They pushed on charged particles, resisting collapse. After recombination, that resistance weakened dramatically. Neutral atoms did not interact with light in the same violent way. Gravity gained the upper hand. This shift allowed tiny differences in density, seeded in the earliest moments of the universe, to begin growing. Slightly denser regions pulled in more matter. Slightly emptier regions grew emptier still. Over millions of years, these gentle imbalances deepened, eventually leading to the first stars and galaxies. Without recombination, none of this could have happened. A universe filled only with free electrons and blazing radiation cannot form structure. It remains smooth, energetic, and sterile. Recombination unlocked complexity by allowing matter to persist. There is something quietly profound about that. The universe did not become structured through force or violence at this stage, but through cooling, through patience, through letting go of excess energy. Stability emerged not from action, but from restraint. Even the timing of recombination reflects this gentleness. It was not synchronized perfectly everywhere. Different regions cooled at slightly different rates. Atoms formed gradually across space, not all at once. Yet the overall transition was remarkably uniform, leaving behind a universe that was astonishingly smooth, with variations of only 1 part in 100,000. Those tiny variations are visible in the cosmic microwave background today as faint temperature differences. They are the fingerprints of recombination, the earliest map of structure ever made. From them, scientists can reconstruct the universe's composition, age, and geometry with remarkable precision. In this way, recombination did more than change the universe's appearance. It preserved its memory. The light released then carries information about the conditions of that era, frozen into its subtle patterns. When modern instruments measure this background radiation, they are not just observing ancient light, they are reading the universe's earliest stable record. For you, listening now, recombination may feel distant, abstract, almost unreal. But everything familiar traces back to it. Every atom in your body exists because electrons learned how to stay. Every star owes its formation to the transparency that followed. Every night sky is possible because light was finally allowed to travel. It is easy to imagine the Big Bang as the universe's defining moment, but recombination was equally transformative. The universe did not merely expand into emptiness. It learned how to organize itself, how to preserve information, how to allow cause and effect to stretch across space. And yet, even after recombination, the universe was still dark. Transparent does not mean illuminated. Stars would not ignite for tens of millions of years. Galaxies would take hundreds of millions more. Recombination did not bring light sources. It brought the ability for light to exist meaningfully. This distinction matters. Recombination was not the birth of brightness, but the birth of visibility. The universe became something that could be seen, mapped, remembered. As this chapter closes, one quiet realization lingers. The first stable atoms did not announce themselves. They did not demand attention. They simply endured. And by enduring, they reshaped everything that followed. As we continue this quiet journey, one question naturally remains. Once atoms existed and light could travel freely, how long would it take before gravity sculpted the first stars from this newly calm and transparent universe? Part 7. Why did light suddenly decouple from matter? Before atoms formed, light and matter were locked together, endlessly exchanging energy. But once electrons found stable homes around nuclei, photons were released from that grip. They streamed outward in all directions, untouched, uninterrupted. That ancient light still exists today, stretched thin by expansion, now observed as the cosmic microwave background. It is the oldest light you can ever see. To understand why this decoupling happened, you must imagine the universe just before this moment. Space was filled with a dense, glowing fog. Not fog made of droplets, but of charged particles. Free electrons drifted everywhere, lightweight and restless. Protons, heavier and slower, moved through the same space. Photons, particles of light, could not travel far at all. Every time a photon tried to move forward, it struck an electron and scattered, changing direction, losing coherence, never escaping. This constant interaction made the universe opaque. Even though it was filled with light, that light could not go anywhere. There was no clear line of sight. No distance light could cross without interruption. In a very real sense, the universe could not see itself. This state is known in physics as a plasma. A plasma is a gas so hot that electrons are stripped away from their nuclei. It conducts electricity, responds strongly to electromagnetic forces, and interacts intensely with radiation. The early universe was not just hot. It was a perfect cosmic plasma, filling all of space, binding light and matter into a single turbulent system. As long as electrons remained free, photons remained trapped. But the universe was expanding. Expansion did not push matter outward into empty space. Space itself was stretching. As it stretched, the energy density dropped, temperatures fell. Photons lost energy, their wavelengths growing longer, their intensity softening. Electrons slowed, protons drifted more gently. Collisions became less violent, less frequent. Eventually, the balance tipped. At around 380,000 years after the Big Bang, the temperature of the universe dropped to roughly 3,000 Kelvin. This number matters. Above it, photons carried enough energy to knock electrons away from protons. Below it, they no longer could. The universe crossed a quiet threshold where ionization stopped dominating and neutrality became possible. Electrons began to settle. When an electron binds to a proton, it forms a neutral hydrogen atom. Neutral atoms interact with light very differently than free charges do. A free electron is an excellent scatterer of photons. A neutral atom, by contrast, is mostly transparent. It can absorb and emit light at specific wavelengths, but it does not constantly deflect every passing photon. As more electrons found stable orbits, the number of free electrons plummeted. The fog thinned rapidly. The universe did not change its appearance gradually. From the perspective of photons, it changed almost all at once. This is the moment of decoupling. Decoupling does not mean light and matter stopped interacting entirely. It means they stopped being locked together. Before this moment, photons and electrons behaved like dancers bound arm to arm, each movement of one forcing a response from the other. Afterward, the dancers separated. Matter continued its slow gravitational evolution while light raced ahead, free at last. Those photons did not disappear. They have been traveling ever since. As the universe expanded, their wavelength stretched. Light that was once visible cooled into infrared, then into microwave radiation. Today, that same ancient light fills the universe uniformly, arriving at Earth from every direction. It has been measured with extraordinary precision and mapped in exquisite detail. Scientists call it the cosmic microwave background. But this light is more than a relic. It is a snapshot. Because photons decoupled at nearly the same time everywhere, the cosmic microwave background preserves an image of the universe as it was at that exact moment. Not stars, not galaxies, but subtle variations in density, tiny ripples in temperature, differences of just 1 part in 100,000. These variations matter deeply. Where the universe was slightly denser, gravity would later amplify that density. Matter would collect, gas would cool, stars would ignite, galaxies would form. Where it was slightly less dense, space would remain more empty. The large-scale structure of the universe, is written into this ancient light. In this way, decoupling did more than free photons, it froze information into the cosmos. Before decoupling, pressure from radiation resisted gravity. Photons pushed back against collapsing matter, smoothing out fluctuations. After decoupling, that pressure vanished. Matter was finally free to respond to gravity alone. This change allowed structure to grow. The universe transitioned from a radiation-dominated era to a matter-dominated one. This shift was subtle but decisive. It marked the end of the universe's earliest phase and the beginning of its long, slow path toward complexity. Without decoupling, the universe would remain a glowing fog forever, unable to form stars, planets, or life. It is worth pausing here. Every photon in the cosmic microwave background has been traveling for nearly 14 billion years. It has crossed expanding space, passed through forming galaxies, slipped between clusters of dark matter, and finally reached your location right now, carrying a message from a time before any structure existed. When scientists point radio telescopes at the sky, they are not seeing distant objects. They are seeing the boundary of visibility itself. Beyond that surface, the universe was opaque. Light could not travel. There is no earlier image to be had. This is why decoupling defines the cosmic horizon. Before it, the universe was a soundless, lightless interior. After it, the cosmos became transparent, observable, legible. Physics transitioned from an environment ruled by radiation to one governed by gravity. In quiet terms, the universe learned how to let go. And this release was not violent. There was no flash, no explosion, no sudden brilliance. The universe simply became clear. Photons drifted outward, no longer colliding, no longer scattering, no longer forced to share their energy. Light found silence. From that moment on, the universe would never be dark in the same way again. Even today, long after stars have formed and galaxies have aged, that background light remains, whispering beneath everything, a constant, gentle presence. You cannot see it with your eyes, but it surrounds you. Your body is immersed in it. Your planet moves through it. Every breath you take happens within a sea of ancient photons released when the universe was still young and simple. This realization carries a quiet weight. The light that decoupled then is older than every atom in your body except hydrogen. It predates the first star, the first galaxy, the first heavy element. It is the universe's earliest surviving memory. And yet, it is calm, uniform, soft. The decoupling of light from matter did not announce itself. It did not demand attention. It simply happened when conditions allowed, when energy fell low enough, when stability became possible. It is a reminder that the most important transitions in the universe are often the quietest ones. As we continue this journey, another question begins to surface. If light was freed and matter was left behind to clump and cool, what paths did that matter take next? How did these first simple atoms begin the long climb toward stars, chemistry, and eventually life? That story unfolds slowly, patiently, written not in flashes but in gravity's steady pull, guiding matter forward through deep, silent time. Part 8. How can we still observe the first atoms today? When you look at the cosmic microwave background, you are seeing a snapshot of the universe just after the first atoms formed. Tiny variations in temperature reveal slight differences in density, the earliest hints of structure. These faint patterns are not noise. They are the fingerprints of the first stable matter, preserved across nearly 14 billion years of cosmic history. To understand how this is possible, you must imagine light not as something fleeting, but as something archival. Every photon carries memory. It remembers where it came from, what it passed through, and how the universe was shaped at the moment it was released. When atoms first formed and light decoupled from matter, the universe effectively took its first photograph of itself. That image has been traveling ever since, stretched by expansion, cooled by time, but never erased. At the moment of recombination, the universe was around 380,000 years old. That sounds ancient by human standards, but cosmically, it was still an infant. Space was filled almost entirely with hydrogen atoms with a small fraction of helium. There were no stars yet, no galaxies, no planets, just a nearly uniform sea of neutral atoms and the light that had finally been set free. Before this moment, photons could not travel far without colliding with charged particles. Space was opaque, like a dense fog. But once electrons settled into atoms, that fog lifted. Photons suddenly found themselves able to move in straight lines, crossing vast distances without interference. Those photons began their long journey across the universe, carrying with them a precise record of the conditions at that time. As the universe expanded, those photons stretched along with space itself. Their wavelengths grew longer, their energy decreased. What was once brilliant visible and ultraviolet light gradually cooled into infrared, then microwave radiation. Today, that ancient light fills the universe uniformly, arriving at Earth from every direction. It is faint, cold, and extraordinarily old. This is what we call the cosmic microwave background, often shortened to the CMB. It is not coming from a particular place in the sky. It comes from everywhere at once. No matter where you look, you are looking back toward the same moment in cosmic history, toward the surface of last scattering, the boundary beyond which light could not previously escape. The temperature of this background radiation is remarkably consistent, just 2.725 degrees above absolute zero. This uniformity tells us something profound. It tells us that the early universe was incredibly smooth, almost perfectly balanced, but not entirely. And those tiny imperfections are where the story becomes truly interesting. If the early universe had been perfectly uniform, with no variation at all, nothing would have happened next. Matter would have remained evenly spread forever. No stars would have formed, no galaxies would have gathered, no complexity would have emerged. But the cosmic microwave background reveals slight variations, temperature differences of only about 1 part in 100,000. These variations correspond to small differences in density. Regions that were ever so slightly denser than average had slightly stronger gravity. Over billions of years, those tiny gravitational advantages grew. Matter slowly fell inward, clouds condensed, structures formed. Every galaxy, every star, every planet can trace its origin back to those barely perceptible ripples preserved in the CMB. To observe this ancient light, scientists had to build instruments of extraordinary sensitivity. The first accidental detection came in 1965, when Arno Penzias and Robert Wilson noticed a persistent microwave noise that could not be eliminated. It came from all directions. It did not vary with time or season. Eventually, they realized they had discovered the leftover radiation from the early universe itself. Since then, space missions have mapped the cosmic microwave background with increasing precision. Satellites like COBE, WMAP, and Planck measured not only its temperature, but its minute fluctuations across the sky. These maps are among the most important images ever created by science. They are not pictures of objects, but of conditions. They show us how the universe looked before anything familiar existed. When you study these maps, you are not seeing stars or atoms directly. You are seeing the imprint they left on light at the moment they first became stable. The formation of the first atoms changed how light moved, and that change is what made observation possible at all. Without recombination, the universe would still be opaque. There would be no deep sky to observe, no cosmic history written in photons. The cosmic microwave background is sometimes described as the universe's baby picture, but this description barely captures its significance. It is also a fossil, a boundary, and a message. It tells us how fast the universe was expanding, how much matter it contained, how energy was distributed, and how the fundamental forces behaved at that time. Even more quietly, it tells us that the universe remembers, that nothing truly disappears. The first atoms formed once, briefly, in a young cosmos, and yet their formation still echoes across space, arriving gently at your detectors, your instruments, and even your own body. Right now, as you sit or lie still, cosmic microwave background photons are passing through you. They are incredibly weak. They cause no sensation, but they are there, brushing past atoms that formed much later, in stars that would not exist for hundreds of millions of years after the light began its journey. This connection across time is one of the most calming truths in cosmology. You are not separate from the early universe. You are downstream from it. The atoms in your body were assembled long after recombination, forged in stellar interiors. But the stage on which all of that occurred was set by the first atoms and the release of light. The cosmic microwave background also marks a limit. When astronomers look deeper into space, they are also looking further back in time, but they cannot see beyond recombination using light alone. Before that moment, the universe was opaque. Photons could not travel freely. The CMB is the farthest back electromagnetic radiation can carry information. Beyond it lies an earlier era, accessible only through indirect clues. Neutrinos, gravitational waves, mathematical models, but light itself draws a soft boundary, a horizon formed by the first stable atoms. It is a reminder that observation depends on structure, and structure depends on calm. The universe did not rush into complexity. It cooled, it waited. It allowed stability to emerge slowly. Only then could light move freely, carrying with it the story of everything that followed. And so, when scientists study the cosmic microwave background, they are not just studying radiation, they are studying the moment the universe became readable, the moment it transitioned from chaos to memory, from turbulence to transparency. As you rest with this idea, consider how gentle that transition was. No explosion marked the birth of atoms, no flash announced their arrival, just a quiet shift in conditions. A threshold crossed, a universe exhaling enough for electrons to settle and light to pass. Those first atoms no longer exist as they once were. They have been recycled, fused, scattered, and transformed. But the light released in their formation still travels, still whispers, still arrives. And as we continue this quiet journey backward through time, one question naturally follows. If the first atoms made the universe transparent and their imprint still surrounds us, what did that new clarity make possible next? Part 9. Why hydrogen mattered more than anything else. Hydrogen may seem unremarkable, but it became the foundation of everything that followed. Nearly all ordinary matter in the universe began this way. Hydrogen clouds gathered under gravity, slowly thickening, slowly compressing. Without hydrogen stability, there would be no stars, no heavier elements, no chemistry complex enough to build planets, oceans, or life. To understand why hydrogen mattered so deeply, you have to appreciate how little the universe had to work with. After the first atoms formed, roughly 75% of all normal matter was hydrogen, with most of the rest being helium. Nothing heavier yet existed, no carbon, no oxygen, no iron, just simplicity, spread thinly across an expanding cosmos. And yet, that simplicity was not a weakness, it was an invitation. Hydrogen is the lightest atom possible, one proton, one electron, almost no internal complexity. Because of this, it responded to gravity in a way heavier, more complicated atoms never could. Hydrogen gas was easily influenced, easily gathered, easily shaped by the gentle pull of mass across enormous distances. In the quiet darkness after recombination, hydrogen began to drift, imperceptibly at first, toward regions that were just slightly denser than their surroundings. Those density differences were tiny. In the early universe, variations in matter were only 1 part in 100,000. But gravity is patient. Given enough time, even the faintest imbalance grows. Hydrogen atoms began to cluster, not because they were instructed to, but because gravity allowed no alternative. Where there was a little more mass, there was a little more pull. And where there was a little more pull, hydrogen slowly gathered. As you breathe right now, this same principle is at work everywhere. Gravity does not rush, it accumulates. It shapes by persistence, not force. And hydrogen, more than any other element, was perfectly suited to respond. As these hydrogen clouds thickened, they cooled further. Collisions between atoms allowed energy to be radiated away, often in the form of faint photons escaping into space. This cooling made the clouds more compact, which strengthened gravity's hold, which caused further collapse. It was a slow feedback loop, unfolding over tens of millions of years. No explosions, no sudden ignition, just quiet preparation. Eventually, in the densest regions, hydrogen clouds reached a critical point. Pressure and temperature rose in their cores. Atoms moved faster. Collisions became more energetic. And then, for the first time since the universe's earliest moments, a new kind of reaction ignited. Nuclear fusion. Hydrogen atoms began to fuse into helium. This is why hydrogen mattered more than anything else. It was the fuel of the first stars. Inside those early stars, known as population 3 stars, hydrogen did something extraordinary. Under immense pressure and heat, protons overcame their natural electromagnetic repulsion and fused together through the strong nuclear force. This process released vast amounts of energy. Light flooded outward. The first stars turned on, breaking the long cosmic darkness. Without hydrogen, this could not happen. No other element was abundant enough, simple enough, or reactive enough to ignite the universe's first light. Hydrogen was not just present, it was essential. These first stars were unlike most stars today. Because they formed from nearly pure hydrogen and helium, they grew enormous. Some may have been hundreds of times the mass of the sun. They burned hot and fast, living brief, brilliant lives before ending in powerful supernovae. And in those final moments, something new occurred. Heavier elements were forged. Carbon, oxygen, nitrogen, silicon, iron, all were created inside stars that owed their existence to hydrogen. Every atom in your body heavier than hydrogen was formed in stellar furnaces that began with hydrogen collapse. The calcium in your bones, the iron in your blood, the oxygen you inhale, all trace their ancestry back to those first hydrogen clouds. Hydrogen also played another, quieter role. It acted as a cosmic buffer. Because hydrogen atoms absorb and emit radiation at very specific wavelengths, especially the famous 21-centimeter line, they allowed the universe to cool in structured ways. This cooling regulated star formation, preventing everything from collapsing all at once. Hydrogen introduced rhythm into cosmic evolution. Even today, hydrogen remains the most abundant element in the universe. Stars continue to burn it. Galaxies remain filled with it. Vast interstellar clouds of hydrogen stretch across space, glowing faintly in radio wavelengths, mapping the large-scale structure of the cosmos. When astronomers trace the shape of galaxies, they often follow hydrogen first. There's also a deeper reason hydrogen mattered. Its simplicity made complexity possible. With only one electron, hydrogen's chemistry is flexible. It bonds easily. It forms molecules like molecular hydrogen, water, ammonia, methane. These molecules become the scaffolding for chemistry, cooling, and eventually biology. Life, as far as we understand it, requires hydrogen not as a curiosity, but as a necessity. Even water, the substance most closely tied to life, is dominated by hydrogen. 2 hydrogen atoms for every oxygen. The universe did not choose hydrogen for life. Hydrogen simply made life possible by being everywhere. When you consider this gently, it reframes the story of the cosmos. The universe did not begin with complexity. It began with almost nothing. And from that near nothingness, hydrogen carried the weight of everything that followed. As the universe aged, hydrogen continued to shape its fate. Galaxies grew by accreting hydrogen from their surroundings. Star formation rose and fell depending on hydrogen availability. Even the eventual slowdown of star birth, billions of years later, is tied to hydrogen being locked away in stellar remnants or dispersed too thinly to collapse again. In this way, hydrogen defined cosmic time. When hydrogen was plentiful and free, stars were born rapidly. As hydrogen became organized and consumed, the universe matured. Today, we live in a universe still rich in hydrogen, but more structured, more layered, more evolved. And yet, nothing has replaced hydrogen's central role. It remains the quiet backbone of matter, the simplest atom still doing the heaviest lifting. As you rest now, it's worth holding this thought softly. Everything complex you know, every planet, every ocean, every living cell, rests on the quiet success of hydrogen. A single proton and electron bound just tightly enough to last, just loosely enough to react, spread across space in unimaginable numbers. And as our calm journey continues, one question gently rises next. If hydrogen built the first stars and elements, how did the universe move from simple light to the rich structures we see filling the sky today? Part 10. How gravity began shaping structure after atoms formed. Once atoms existed, gravity finally had something to work with. Neutral matter could clump without being torn apart by radiation pressure. Over millions of years, regions slightly denser than their surroundings began to grow. These gentle imbalances were enough. Gravity amplified them patiently, drawing matter inward, laying the groundwork for stars and galaxies yet to come. Before this moment, gravity had been present, but it had little influence. When the universe was filled with free electrons and charged particles, electromagnetic forces and intense radiation dominated. Light pushed back. Pressure smoothed everything out. Any attempt at clumping was erased almost as quickly as it began. But once atoms formed and light decoupled, the universe entered a quieter phase. Gravity, the weakest of the fundamental forces, finally had the silence it needed. Gravity does not act suddenly. It does not announce itself. It works through accumulation, through patience. If one region of space contains just a tiny bit more matter than another, gravity begins to pull inward. The difference can be almost unimaginably small. In the early universe, these density variations were only about 1 part in 100,000. Yet over time, gravity magnified them. You can imagine the universe at this stage as a vast cooling fog of hydrogen and helium. Almost perfectly smooth, but not quite. In some places, atoms were slightly closer together. In others, slightly farther apart. These differences were inherited from the earliest moments of cosmic inflation, frozen into space itself. Gravity simply followed the map that had already been drawn. Where matter was denser, gravity pulled more strongly. That pull attracted even more atoms, deepening the imbalance. The denser regions grew denser, the emptier regions grew emptier. This slow separation is called gravitational instability, and it is the reason structure exists at all. Without it, the universe would remain a thin, featureless haze forever. Importantly, this process required neutrality. Once atoms formed, matter no longer carried large-scale electric charge. Positive and negative charges canceled out. Electromagnetic repulsion faded into the background. Radiation pressure dropped dramatically. Gravity was no longer competing with light. It could finally act across long distances without interference. As millions of years passed, hydrogen clouds began to stretch and drift under gravity's influence. They did not collapse all at once. Instead, they flowed gently, like slow currents in an invisible ocean. Matter moved along the subtle contours of space-time, guided by gravitational wells that were still shallow but steadily deepening. Dark matter played a crucial role here. Although invisible and non-interacting with light, dark matter outweighed ordinary matter by about 5 to 1. Long before atoms formed, dark matter had already begun clumping under gravity. When ordinary matter became neutral, it fell into these pre-existing gravitational scaffolds. Galaxies would later grow where dark matter had already laid the foundation. In this way, gravity was not starting from nothing. It was continuing a process that had been waiting for the right conditions. The formation of atoms was the key that unlocked it. Once matter could move freely without being scattered by photons, it responded to gravity's quiet pull. Over tens of millions of years, the densest regions became clouds vast beyond comprehension. They spanned hundreds of thousands of light years. Inside them, gravity slowly increased pressure and temperature. The atoms inside these clouds drifted closer, colliding gently, exchanging energy, settling deeper into the gravitational well. Nothing dramatic happened at first. No explosions, no light, just gradual thickening. Gravity does not rush. It allows time to stretch. As atoms fell inward, gravitational potential energy converted into heat. Temperatures rose, but still not enough to ignite anything. The universe remained dark. This era is sometimes called the cosmic dark ages, not because nothing was happening, but because nothing was shining yet. The groundwork was being laid invisibly. Every future star, galaxy, and cluster traces its origin to this silent period of gravitational assembly. Eventually, in the densest cores of these clouds, pressure and heat became intense enough to change everything. Hydrogen nuclei moved faster. Collisions grew more energetic. When temperatures reached millions of degrees, nuclear fusion became possible. The first stars were born. But that moment lies ahead. What matters here is that gravity made it inevitable. Gravity does not create complexity on its own. It simply gathers. But gathering is enough. Once matter is brought together, new physics takes over. Fusion, chemistry, radiation, feedback, all of it depends on gravity's initial work. What is remarkable is how little was required. No fine-tuning, no intervention, just a universe slightly uneven, cooling and expanding. Gravity took those imperfections and slowly amplified them into everything we see today. Even now, as you sit still, gravity continues this process on all scales. Galaxies pull on galaxies. Clusters draw together. Matter flows along filaments stretching across hundreds of millions of light years. The universe is still organizing itself, still responding to the same quiet force that began shaping structure shortly after the first atoms formed. When you look up at the night sky, every star you see is a monument to gravity's patience. Each one began as a subtle imbalance, a barely detectable excess of atoms in one region of space. Given enough time, that was enough. And as we continue this quiet journey, one question naturally follows. If gravity built the first stars from simple atoms, what happened when those stars began to change the universe in return? Part 11. Why the first atom didn't create stars immediately. Nothing in the universe happens quickly at this scale. After the first atoms formed, there was a long, dark age. No stars yet burned. Space was filled with cold hydrogen, drifting silently. This quiet period lasted hundreds of millions of years. It was not emptiness, but preparation. The universe was gathering itself. At first glance, it may seem surprising. Atoms finally existed. Matter could remain stable. Gravity had something real to pull on, and yet nothing lit up. No stars ignited, no galaxies appeared. The cosmos remained dark, calm, and almost motionless to the eye. This era is known as the Cosmic Dark Ages, and it is one of the most patient chapters in the universe's story. To understand why stars did not appear right away, you have to consider just how thin the universe still was. Even after recombination, matter was spread incredibly evenly across vast distances. Hydrogen atoms drifted apart, separated by enormous stretches of space. Gravity was present, but it was weak at these densities. It could tug, but only gently. There was no sudden collapse, no dramatic gathering, only an almost imperceptible pull, working over unimaginable spans of time. Imagine standing in a perfectly still fog, where each droplet is so far from the next that they barely notice one another. Even with gravity urging them together, the process would be slow. In the early universe, this slowness was the rule. Density differences were tiny, measured in parts per 100,000. Yet, gravity is relentless. It does not need urgency. It only needs time. As you rest here now, breathing slowly, it may help to remember that gravity operates with infinite patience. It never rushes. It simply accumulates. Those slight overdensities imprinted in the cosmic microwave background, the faint temperature variations we observe today, were the seeds. They were not dramatic. They did not announce themselves. But they were enough. During the Dark Ages, hydrogen atoms began to fall inward toward these slightly denser regions, not in streams or waves, but in quiet drifts. Each atom responded to the combined gravitational influence of countless others. The motion was slow, almost hesitant. 1,000,000 years might pass with barely noticeable change. 10 million more would follow, just as quietly. Another reason stars did not form immediately lies in temperature. Although the universe had cooled enough for atoms to exist, it was still too warm for gravity to easily compress gas into dense clumps. Thermal motion resisted collapse. Atoms moved just fast enough to counteract gravity's pull. To form a star, gas must cool further, shedding energy so it can sink inward more efficiently. That cooling takes time, and it requires specific physical processes. In these early epochs, there were no heavy elements, no carbon, no oxygen, no dust grains. Modern star formation relies on these elements to radiate heat away efficiently. Early hydrogen clouds lacked these tools. Cooling was possible, but inefficient. The universe had to wait until gravity slowly increased densities, enough for even hydrogen alone to cool and collapse. There is also the matter of scale. The first stars were not born from individual atoms or small clouds. They required vast reservoirs of gas spanning many light years. Building such structures from an almost uniform universe is like trying to form mountains from a calm ocean. It can be done, but only through persistent cumulative forces acting over immense time. As hundreds of millions of years passed, dark matter played a crucial role. Though invisible, dark matter began clumping earlier than ordinary matter because it did not interact with light. It formed gravitational wells, deep but silent. Hydrogen gas gradually fell into these wells, collecting slowly. Without dark matter, the first stars might never have formed at all, or might have taken far longer than they did. This period of darkness was not static. It was dynamic in the quietest possible way. Every second, every year, every millennium, gravity was doing its work. Hydrogen clouds grew denser. Temperatures in their cores dropped. Motion became more ordered. The universe was practicing the delicate balance required for ignition. And ignition is not simple. A star does not begin with fire. It begins with pressure. As gas collapses inward, density rises. Collisions between atoms become more frequent. The core grows hotter, not because of combustion, but because of compression. Only when temperatures climb into the millions of degrees does nuclear fusion begin. That threshold is high. Reaching it requires enormous mass and sustained collapse. The first stars, when they finally formed, were unlike the stars you see today. They were massive, short-lived, and intensely bright. But before they could exist, the universe had to assemble the right conditions with exquisite care. The Dark Ages were the universe learning patience. There is something deeply soothing about this realization. Creation was not a sudden flash after atoms formed. It was a long pause, a quiet gathering, a time when nothing dramatic happened, yet everything important was underway. The universe was not idle. It was becoming ready. If you could float through space during this era, there would be no light to guide you, no stars to mark distance, only faint afterglow radiation already stretched into invisibility, and endless hydrogen drifting in the dark. And yet, within that darkness, the future was inevitable. Eventually, in the densest regions, gravity overcame resistance, clouds collapsed faster, cores heated, and one by one the first stars ignited, ending the Dark Ages and flooding the universe with light once more. But that story belongs to the next chapter. For now, it is enough to rest with this truth. The first atom did not create stars immediately because the universe moves on timescales far gentler than urgency. It builds complexity slowly. It allows silence. It waits until conditions are just right. And as we continue this quiet journey, one question naturally follows. What finally broke the darkness, and how did the first light return to the universe? Part 12. How the first atoms led to the first stars. Eventually, gravity won its slow contest. Hydrogen clouds collapsed until their cores grew hot enough to ignite nuclear fusion. The first stars were born, massive and short-lived, forging heavier elements in their cores. But none of that could happen without the earlier moment when electrons and protons first agreed to stay together. 2. Understand how atoms became stars, you have to slow your sense of time even further. After recombination, after the universe became transparent and dark, nothing dramatic happened for a very long while. There were no sudden flashes, no fireworks in the sky. Instead, there was patience. The universe entered what cosmologists call the cosmic dark ages, a period where matter existed, but light sources did not. Space was filled with neutral hydrogen and helium atoms, drifting through expanding darkness. These atoms were not evenly spread. From the very beginning, the universe had tiny imperfections. Slight differences in density, imprinted in the earliest moments and preserved in the cosmic microwave background, meant that some regions contained just a little more matter than others. The difference was minuscule, sometimes only 1 part in 100,000. But gravity is relentless. Where there's even a slight excess of mass, gravity pulls inward, however gently. Imagine floating in a perfectly still ocean, where some regions are just barely thicker than others. At first, nothing seems to move. But over millions of years, those slightly denser regions begin to draw in their surroundings. Hydrogen atoms drift closer together, their motions slowing as gravity nudges them inward. There is no sound, no friction as we know it, just a gradual gathering, guided by an invisible force that never switches off. In the early universe, radiation pressure had once pushed matter apart, preventing collapse. But now, with atoms neutral and light decoupled, that pressure had faded. Gravity finally had the quiet conditions it needed. Neutral hydrogen did not repel itself electromagnetically the way charged particles do. It could fall inward freely, responding only to gravity's patient pull. As clouds grew larger, their gravitational grip strengthened. More atoms were drawn in, the cloud became denser, and as density increased, so did temperature. This heating was not caused by fire or fusion, but by compression. When atoms fall inward, gravitational energy is converted into heat. Slowly, steadily, the center of these clouds warmed. For tens of millions of years, nothing visible happened. The universe remained dark, lit only by the faint afterglow of the Big Bang stretching thinner with each passing moment. But deep within these gathering clouds, conditions were changing. Hydrogen atoms collided more frequently. Speeds increased. Temperatures climbed from just a few degrees above absolute zero to hundreds, then thousands of degrees. Eventually, in the densest regions, gravity pushed matter far enough that atoms could no longer remain intact. Electrons were stripped away once more, not by cosmic heat this time, but by crushing pressure. Hydrogen became plasma again, but now in a very different environment. This was no longer a universe-wide furnace. This was a localized collapse, a single cloud tightening its grip. At the very core of these collapsing clouds, temperatures reached millions of degrees. Protons moved fast enough to overcome their natural electrical repulsion. When they collided, they fused. Hydrogen nuclei merged to form helium, releasing energy in the process. For the first time since the universe began, a new source of light was born. This was the ignition of a star. The first stars, known as population 3 stars, were unlike anything that exists today. They were made almost entirely of hydrogen and helium, with no heavier elements at all. Because of this simplicity, they behaved differently. Without heavier elements to help cool the gas, these stars grew enormous. Many were tens or even hundreds of times more massive than the Sun. Their size made them bright and short-lived. They burned through their fuel rapidly, shining intensely for only a few million years before exhausting their cores. But during those brief lives, they changed the universe forever. In their hearts, nuclear fusion created the first heavier elements: carbon, oxygen, nitrogen, and beyond. When these massive stars died, often in violent supernova explosions, they scattered those elements into space. This enrichment was essential. Heavier elements allowed gas clouds to cool more efficiently, fragmenting into smaller clumps. That cooling process made it possible for smaller, longer-lived stars to form later on. It also laid the groundwork for planets, chemistry, and eventually life. But every step of that story traces back to hydrogen, to the first atom, and to gravity's ability to gather it. There is a profound quietness to this chain of events. From the first stable atom to the first star, hundreds of millions of years passed. The universe did not rush. It assembled complexity slowly, layer by layer, governed by simple rules applied over immense stretches of time. Electromagnetism allowed atoms to form. Gravity allowed them to gather. Nuclear physics allowed stars to shine. Even now, as you sit quietly, those same rules are at work. The atoms in your body were once part of ancient stars, but before that, they were hydrogen drifting through darkness. Before that, they were electrons and protons finally finding stability. The story is continuous, unbroken, stretching back to the universe's earliest calm moments. As the first stars ignited, their light began to transform the cosmos. Ultraviolet radiation poured outward, ionizing surrounding hydrogen, ending the dark ages. Galaxies began to assemble around these early beacons. Clusters formed. Structure emerged on grand scales. But all of it depended on that initial step, the universe learning how to make matter that could last. When you think of the first atom, it is easy to imagine it as small and insignificant. Just one proton, one electron. But in reality, it was a turning point. It marked the moment when the universe became capable of complexity. Without atoms, there are no clouds. Without clouds, no stars. Without stars, no elements. Without elements, no worlds. And yet, the process itself was gentle. No single atom knew it would become part of a star. No cloud rushed toward collapse. Everything followed the quiet guidance of physical law. Gravity did not demand urgency. It simply waited, confident that given enough time, matter would gather. As we continue this quiet journey, one question naturally follows. If the first stars reshaped the universe so completely, what happened to the darkness they emerged from? And how did that darkness give way to the luminous cosmos we see today? Part 13. Why complexity begins with simplicity. The universe did not start with variety. It started with repetition, hydrogen atoms again and again filling space. From that sameness emerged everything else. Complexity was not imposed from the start. It unfolded gradually, built layer by layer upon a foundation of stability, patience, and time. If you could drift through the universe after the first atoms formed, you would not see a rich tapestry of matter. You would see almost nothing at all. Vast regions of darkness, lightly dusted with identical atoms, all behaving in nearly the same way. No colors, no solids, no chemistry as we know it. Just hydrogen, neutral, and quiet spread thin across an expanding cosmos. And yet, within this extreme simplicity lay the potential for everything that would ever follow. In physics, simplicity is not a weakness. It is often the most stable state a system can achieve. Hydrogen is the simplest atom possible because it is the smallest balance that can exist. One proton, one electron, held together by the electromagnetic force. There is no redundancy, no excess structure. And because of that, it is remarkably resilient. Once the universe cooled enough for hydrogen to form, it did not easily break apart again. The chaos of the early universe had finally given way to a pattern that could endure. This endurance is what made complexity possible at all. Complex systems cannot survive in unstable environments. They require time. They require consistency. They require rules that do not change abruptly. Hydrogen provided that consistency. Its behavior was predictable. Its interactions were governed by well-defined physical laws. Wherever hydrogen existed, the same rules applied. This uniformity allowed the universe to evolve without tearing itself apart. You can think of complexity not as something added suddenly, but as something that accumulates. Each new layer depends entirely on the stability of the layer beneath it. Without stable atoms, there can be no molecules. Without molecules, no chemistry. Without chemistry, no stars that forge heavier elements. Without those elements, no planets. And without planets, no environments where life might eventually arise. Each step is built upon the quiet success of the one before it. In the early universe, gravity was the first force to take advantage of this simplicity. Hydrogen atoms, being electrically neutral, could drift closer together, without repelling one another. Over immense stretches of time, slight variations in density grew more pronounced. Regions with just a little more hydrogen began to pull in their surroundings. This process was slow, almost imperceptible, but relentless. Gravity does not need urgency, it only needs time. As these hydrogen clouds thickened, temperature and pressure increased at their centers. Eventually, conditions became extreme enough to ignite nuclear fusion. Hydrogen atoms began to combine, forming helium and releasing enormous amounts of energy. This was the birth of the first stars, and with them, the universe took its first step toward chemical diversity. But it is important to remember that none of this would have been possible without the earlier era of simplicity. The stars did not appear because the universe was complex. They appeared because it was simple for long enough. The same pattern repeats at every scale. In stellar cores, simple reactions dominate before more complex ones can occur. In planetary formation, basic materials condense before they differentiate. Even in biological systems, the earliest life forms were structurally simple, relying on repetition and redundancy rather than specialization. Complexity emerges not from chaos, but from order sustained over time. There is a quiet lesson here, written into the structure of reality itself. The universe does not rush toward intricacy. It allows it to grow. It permits simple systems to persist, to interact, to combine in small ways until something new becomes possible. This is not inefficiency. It is stability. A universe that had tried to become complex too quickly would have destroyed its own progress. Hydrogen's simplicity also made it abundant. During the first few minutes after the Big Bang, when protons and neutrons first assembled into nuclei, conditions favored the creation of hydrogen far more than any other element. Heavier elements require precise conditions and intermediate steps. Hydrogen requires almost nothing at all. As a result, it came to dominate the universe's composition. Even today, most of the visible matter in the cosmos remains hydrogen, quietly fueling stars and tracing the large-scale structure of galaxies. This abundance mattered. When stars formed, they formed primarily from hydrogen. When galaxies assembled, their mass was defined by vast hydrogen halos. Even now, when astronomers map the universe at the largest scales, they often do so by tracking hydrogen emissions. The simplest atom remains the backbone of the most complex structures ever observed. If you step back and consider this, there is something deeply calming about it. The universe did not require elaborate initial conditions to become what it is. It did not need fine detail from the start. It needed only a few stable rules, applied consistently, and enough time for those rules to play out. Complexity was not planned, it was permitted. Even the laws of physics reflect this preference for simplicity. At their core, they are remarkably concise. A small set of equations governs an enormous range of phenomena. From the behavior of electrons in atoms to the motion of galaxies across billions of light years, the same fundamental principles apply. This economy of rules is what allows complexity to emerge without becoming incoherent. As you breathe now, surrounded by materials forged in stars, built from atoms heavier than hydrogen, it is easy to forget how much depended on that first simple success. The moment when electrons and protons first remained together was not dramatic. It produced no light, no sound, no immediate spectacle. And yet it was one of the most important transitions the universe ever made. It marked the point at which matter became reliable, and reliability is what makes growth possible. Whether in physics, chemistry, or life, stable foundations allow exploration. They allow variation without collapse. They allow new arrangements to form and persist. The universe's path toward complexity was not driven by ambition or acceleration, but by patience. As this chapter of the story draws to a close, one quiet realization remains. Everything intricate you have ever known traces back to an era of profound simplicity, to a universe content, for a long time, to be almost the same everywhere. And as we continue this gentle journey forward, the next question waits naturally in the dark. If simplicity was enough to begin everything, what does that say about how much more can still emerge, given time? Part 14. What the first atom teaches us about existence. The first atom reminds us that profound change does not require drama. Sometimes it only requires conditions to become gentle enough. The universe did not force matter into existence. It waited until matter was ready. In that waiting, everything you know was made possible. When you think about the birth of the first atom, it is tempting to imagine a moment of brilliance, a flash, a turning point marked by spectacle. But the truth is quieter than that. There was no single instant when the universe announced its achievement, no sound, no light flaring into being. Instead, there was a gradual easing, a softening of the cosmic environment until stability was no longer forbidden. For hundreds of thousands of years, the universe simply expanded and cooled. It did not rush. It did not hesitate. It followed the steady logic of physical law. Energy thinned out, distances grew, temperatures fell, and when the chaos had diminished enough, matter discovered that it could finally rest. This is the first lesson the atom offers. That structure arises not from force, but from balance. The proton and the electron did not conquer one another. They did not collide violently and lock together. They settled, they remained. They found a configuration that could last. In physics, stability is not about strength, it is about permission. The early universe did not allow atoms to exist because it was too hot, too crowded with energy. Once that energy diluted, the same particles that had always existed were suddenly free to behave differently. Nothing new was added. Only the conditions changed. That idea echoes far beyond cosmology. It suggests that many transformations are not created by introducing something extraordinary, but by removing what prevents stability from emerging. The universe did not invent matter at recombination. It allowed matter to be itself. As you breathe quietly now, you are surrounded by atoms that trace their lineage back to that first moment of permission. The hydrogen in your body, the oxygen in the air, the carbon that forms your cells, all of it required that initial act of cosmic patience. Without the first atom's success, complexity would have remained impossible. There is also a lesson here about time. The universe did not hurry. From our perspective, waiting nearly 400,000 years for atoms to form might seem excessive, but on cosmic scales, it was simply the natural pace of cooling and expansion. Time was not an obstacle, it was an ingredient. In modern life, we often treat time as something to overcome, something to compress, something standing between us and outcomes. But the universe teaches a different relationship. Some things can only happen slowly. Some forms of order require duration, not urgency. The first atom also reminds us that simplicity is not a flaw. Hydrogen was not impressive. It had no complexity, no diversity, no chemistry beyond the most basic interaction. And yet, it was enough. From hydrogen came stars. From stars came heavier elements. From those elements came planets, water, biology, thought. Nothing about hydrogen predicted the richness that would follow. And yet, everything depended on it. In this way, the first atom becomes a lesson in emergence. The universe did not plan galaxies when hydrogen formed. It did not design life when electrons settled into orbit. Those outcomes were not encoded as blueprints. They emerged naturally as stable matter interacted with gravity, energy, and time. Existence unfolded rather than executed. There is a quiet humility in that realization. The universe did not aim for complexity. It allowed it. And once allowed, complexity took care of itself. The first atom also teaches us something about connection. Before atoms, particles interacted constantly but could not remain together. Bonds were temporary. Relationships dissolved as quickly as they formed. With the first atom, permanence entered the universe. Not eternal permanence, but persistence. The ability for something to last longer than a fleeting interaction. That persistence made memory possible. Structures could now carry information forward in time. Patterns could accumulate rather than reset. Without that persistence, the universe would have remained a flickering sea of interactions with no history. Atoms gave the cosmos a way to remember. Every molecule is a record. Every crystal lattice is a pattern that endured. Every biological system is built on structures that hold long enough for complexity to layer itself upon them. Memory, in the deepest physical sense, begins with the first atom. There is also comfort in how unremarkable this moment was. The universe did not change its rules. It did not break its own laws to create matter. The same equations that governed chaos governed stability. Nothing special had to be added. Only patience. This suggests that the universe is not hostile to order. It is neutral, even generous given time. Chaos dominates early when energy is dense and motion is extreme. But as expansion continues, calm inevitably follows. From that calm, structure grows. As you lie here listening, your own body reflects this history. You are not a violation of the universe's nature. You are a continuation of it. The same physics that allowed electrons to settle into orbit allows neurons to fire, cells to divide, and consciousness to emerge. The first atom did not know what it would become part of, and neither did the universe. There is something deeply reassuring about that. Existence did not require foresight. It required conditions gentle enough for stability to take hold. Everything else followed. In that sense, the first atom teaches us about inevitability, not as destiny, but as possibility. Given time and the right conditions, complexity is not rare, it is natural. The universe did not rush to create stars. It did not hurry toward life. It moved at a pace dictated by physics, and along that path, moments of stability appeared. Each one opened new doors. The first atom was the first door. Once it opened, the universe could never return to its earlier state. Transparency replaced opacity. Matter replaced plasma. Structure replaced turbulence. From that point forward, the cosmos had a memory and a future, and yet the transition itself was almost invisible. No fireworks, no announcement, just electrons staying close to protons a little longer than before, light slipping free, space growing quieter. If you imagine that moment, it does not feel like a beginning. It feels like a settling, like dust drifting down after a storm, like silence returning to a room. Perhaps that is the deepest lesson of all, that beginnings are not always loud, that the most important changes often happen when things slow down, not when they accelerate. The universe became what it is not through force, but through release. It let go of excess energy. It allowed motion to soften. It gave matter the chance to stay. As this part of the story comes to rest, you can carry that lesson with you. That stability is not weakness. That patience is powerful. That waiting is sometimes the most creative act of all. Because once the universe learned how to hold itself together, it never stopped building upon that success. Part 15. Why this moment still matters to you. Every atom in your body traces its history back to that first, successful bond. The calm arrangement of electrons around nuclei is not just ancient physics. It is happening inside you right now, holding you together, quietly, reliably. The first atom was not just the beginning of matter, it was the beginning of continuity. And that continuity has never been broken. To understand why this moment still matters to you, it helps to pause and feel how effortless existence seems. You are not consciously holding yourself together. Your bones do not need instructions to remain solid. Your skin does not negotiate each second whether it should stay intact. All of that stability is granted freely, moment by moment, by the same physical agreement first reached when the universe was young enough to remember its own beginning. At its core, you are an arrangement of atoms that have learned how to coexist. Electrons orbit nuclei in patterns dictated by quantum rules that have not changed in nearly 14 billion years. These rules do not age, they do not weaken, they do not forget. The hydrogen atom that formed shortly after recombination followed the same principles that govern the atoms composing your thoughts right now. The universe has been consistent with you from the very start. When the first atom formed, it established a precedent. It showed that energy could settle, that chaos could soften into structure, that balance was possible. That same balance is what allows your body temperature to remain stable, your cells to maintain their shapes, and your nerves to transmit signals without tearing themselves apart. The quiet physics of atomic structure is not background scenery. It is active, continuous, and deeply intimate. Every breath you take depends on it. Oxygen atoms bind with hemoglobin in your blood because electrons can share space without collapsing inward or flying apart. Chemistry itself is only possible because atoms can remain whole long enough to interact gently. If electrons were even slightly less stable in their orbits, molecules would unravel before they could do anything useful. Life would never have found a foothold. And yet, this stability is not rigid. It is flexible in exactly the right ways. Atoms can bond, separate, rearrange, and recombine without losing their identities. That balance between permanence and change is what allows you to grow, heal, and adapt. It is the same balance the universe discovered when it first cooled enough to let electrons stay close to nuclei without being destroyed by light. There is something quietly reassuring in that. The laws that keep you intact are not fragile. They survived the early universe when temperatures were unimaginable and space itself was stretching faster than thought. They survived the collapse of stars, the formation of galaxies, and the long dark ages before light returned. They are still here, still working, still dependable. Even as you rest, trillions of atoms inside you are vibrating gently, exchanging energy, maintaining structure. This motion is not chaotic. It is regulated, rhythmic, and precise. It is a continuation of the same cosmic rhythm that began when the universe first learned how to cool itself into matter. In a very real sense, you are not separate from that moment. You are an expression of it. When you feel calm, when your breathing slows, when your body settles into stillness, you are mirroring the same transition the universe once made. From turbulence to balance, from noise to structure, from endless collision to quiet persistence. The universe learned how to rest without falling apart, and that lesson lives on in you. It also offers perspective. The challenges and disruptions of daily life feel large because they occur on human scales of time and emotion. But beneath all of that, the deeper structure of reality remains unchanged. The atoms composing your worries are held together by the same calm rules as the atoms composing your peace. No thought, no fear, no uncertainty alters the basic stability of matter itself. That does not diminish your experiences, it grounds them. It reminds you that beneath every moment of change, there is a foundation that does not shift. The continuity that began with the first atom has carried everything forward without interruption. Civilizations rise and fall, stars ignite and fade, but the rules that allow matter to exist remain steady. Even death does not break that continuity. Atoms do not vanish when life ends. They disperse, recombine, and continue participating in the universe's long story. The carbon in your body was forged in ancient stars. The hydrogen in your cells has existed since near the beginning of time. You are temporary as an arrangement, but eternal as material. The first atom matters because it marked the moment the universe became capable of memory. Before atoms, nothing could last. After atoms, information could be stored in structure. Patterns could persist. Eventually, those patterns grew complex enough to reflect on themselves, to wonder, to listen, to rest. Right now, as you lie still, the same physical agreements are being honored. Electrons remain where they should. Nuclei hold together. Forces balance without effort. You do not need to supervise any of it. The universe is still keeping its promise. And that promise is simple. If conditions are gentle enough, stability will follow. If patience is allowed, structure will emerge. The universe did not rush into complexity. It waited. And because it waited, everything that followed was possible. As this thought settles, you may notice how little you need to do to exist in this moment. The continuity that began with the first atom is carrying you effortlessly forward. You are held by the same laws that once allowed light to travel freely for the first time. And as this quiet journey continues, one final understanding remains softly present. You are not separate from the universe's beginning. You are part of its longest, calmest sentence, still being written, one stable atom at a time. As we come to the end of this quiet journey, it's worth resting for a moment with the scale of what you've just followed. From a universe too hot to hold even the simplest bond, to a single proton and electron learning, for the first time, how to remain together. From that fragile stability came atoms, then darkness, then stars, then planets, then eventually the calm complexity of life itself. Nothing rushed, nothing forced. Everything unfolded when the conditions were ready. The first atom did not announce itself. It did not glow or explode or declare a beginning. It simply stayed, and in staying, it allowed everything else to follow. As you lie here now, breathing slowly, that same quiet physics is still at work. Electrons still orbit, atoms still hold, forces still balance with extraordinary precision. The universe has not stopped becoming. It has only learned how to do so gently. If this story brought you even a small sense of calm or wonder, I'm deeply grateful you spent this time here. A gentle like, a quiet tap on subscribe, or your thoughtful presence means more than you know. It helps keep this small corner of stillness alive. For now, you don't need to carry any more questions. The universe has already done the work. You can rest inside its continuity, knowing that the same laws that shaped the first atom are holding you safely together tonight. Thank you for being here. Sleep softly.